We're going to combine chapters 10 and 11. Actually, they're already combined. They deal with the same thing, Lewis structures. But let me finish up with chapter 9. What were the important things from chapter 9 that we covered? You know, size of atoms and size of ions. You know, size of atoms and ions are important for reactivity, also for bonding, which is a topic for 10 and 11. And so we talked about size and electron configuration. So we'll be using these concepts throughout. And as far as what sizes do you have to memorize? Were there any sizes? No, just ballpark, you know, about how big are atoms. 53 picometers is on the small side, but generally if you were to average it, it would be about 100 picometers, maybe 100, 200, 100 picometers is good. So we have the size, and then what else did we talk about? We talked about, yeah, but in relation to ionization energy. We had, you know, I1, I2, etc. So we're looking at the ionization. The funny thing about the ionization energies was this. The ionization energies were for the gaseous atoms. And that was it. It's always a gaseous atom or ion being ionized. So we have the ionization energy, and then...
Wait, you said ionization energy is for gaseous atoms?
Yeah,
only?
gaseous
What do you
atoms.
mean?
Yeah.
And so the general equation is A gas goes to A plus gas, where A is just whatever atom you're trying to ionize, an electron. This would be ionization. This was ionization 1. What would ionization energy 2 be? It'd be taking A plus gas and knocking another electron off. Yeah, we'd end up with a 2 plus ion. So that would be ionization energy. And so ionization energies typically follow the size trends. You know, the bigger an atom is, the easier or the harder it is to ionize.
Easier.
The easier it is. So, then we had something called electron affinity. What do we use electron affinity for? Well, electron affinity is when we take a gaseous atom and add an electron to that to form the anion. This is also going to be in the gaseous state. And that would be EA1 or E1, whatever you want to call it. So we use E for energy. I use EA for electron affinity.
So you say that the bigger the size, the easier to ionize.
The bigger it is, the easier it is to ionize. Yeah. Bigger. You're going to pull off the outermost electron. And so this goes, you know, if there's an electron in an atom here, electron in an atom here, which one? An oxidizer comes along, which one do you think will be easier to?
The big one.
The big one, yeah.
Oh, I have a question. I have here, how do you figure out the real charge?
The real charge on an atom?
Yes.
The way you figure out the real charge is, one, you do some quantum mechanical calculations, or two, you guesstimate it. That's how we do it.
Okay.
This is the one we talked about yesterday, right? Where you set 1 to 0 and assume, right?
Kind of, yeah. Now, there is another way to do this, and that's experimentally determine it. They can experimentally determine the real charge on an atom by measuring something called its dipole moment. Its dipole moment is the amount that the charge is separated. It behaves like a little dipole. You know what a dipole is? Yeah. Two poles. A dipole is like, everybody's familiar with one dipole, a magnetic dipole. I mean, a magnetic dipole, you have a north pole and a south pole. But we could have electric dipoles too. In an electric dipole, you have a positive pole and a negative pole. And so that's what a dipole is. It has two poles. A quadrupole, have you heard of quadrupoles? Quadrupoles have 4 or more poles. And so you can actually have a magnet with 2 north poles and 2 south poles, or more. And so we have electron affinity. Electron affinity, we don't necessarily use that so much. Other than thermodynamic calculations. So, you know, for example, which element has the highest electron affinity? If you think about affinity, affinity would be love. And so which atom has the highest love for an electron? I would say fluorine. You know, but this is one of those tricks. It turns out fluorine doesn't have the highest electron affinity. It is not helium. It's chlorine. Did I talk about why chlorine has a higher electron affinity than fluorine? No? How much of electron affinity did I talk about?
Nothing.
Nothing? How much of ionization energy did I talk about?
A little.
A little bit? So we looked at the ionization energies, and we saw the ionization energies for the valence electrons compared to the core electrons. Okay, so this is where we left off. This is electron affinity, so let's talk about that. It would follow the same. You know, we always add 1 electron at a time. So EA1 would be 1 electron. EA2 would be taking this ion and adding an electron to that to form the 2 minus. Yeah, so this is EA2. Now, electron affinities, these tend to be endothermic or exothermic, because when we think about ionization energy, it always costs you energy to take an electron away. But when we add an electron, it turns out that most EAs, this is the general trend, most EA1s are exothermic, meaning it's favorable. Even for example, sodium, you know, it costs you about 500 kilojoules per mole to ionize a mole of sodium atoms, gas, to create sodium ions. But if we were to add an electron to form this is a very unusual ion, isn't it? This would actually be exothermic, meaning it's forming something more stable. And so this is EA1, which is less than 0. The sodium. Now, if we go to something like beryllium, you know, if we add an electron to beryllium, it's not so favorable, beryllium gas. EA1 is greater than 0. Okay, so the thought goes like this. To add it to sodium, there's space in the 1s, or not 1s, sodium would be the 3s orbital. There's space in the 3s orbital to accommodate that electron, right? And there's already a 3s electron, so is a 3s electron good at shielding? So if we got another 3s electron here, this would go in the 3s orbital, is that existing 3s electron in the sodium orbital going to shield this? No. Same, you know, same shell is not very effective shielder. And so this electron is going to feel some Z effective, and that Z effective is going to hold it on, and this is what creates this stabilizing energy. Whereas now, when we look at beryllium, beryllium is existing 2 electrons in the 2s orbital. And so this electron doesn't go into the 2s orbital. This electron has to go into the 2p orbital. Now, 2s or 2p, which one's more penetrating? 2s, so the 2p is not going to be as stable as a 2s, and therefore we see it here. But when we go from beryllium to boron, when we go to boron and add an electron here, then it turns out to be exothermic, EA1. And so this is an exception here. Beryllium's an exception. You know, most are exothermic except for beryllium and other group 2 elements. And so the entire group 2 elements are going to have a positive electron affinity. What else can you think wouldn't really like another electron?
Noble gases.
Noble gases. The noble gases have, like helium. Helium does not want an electron, because that electron would have to go in the next shell, and so EA1 is highly endothermic. Endothermic means we're going up in energy, it's becoming less stable. So, no, in fact, all the noble gases have low electron affinity.
So a low electron affinity means positive?
Yeah. Yes. Yes. How does Petrucci explain it? You could read it.
No. Just stick with yours.
Yeah, I'll read it. Yeah, low electron affinity means more endothermic, less energetically favorable. Does that make sense? Okay. Not yet. Anyway, we like to go down in energy. Going down in energy is always good because we're going to things that are more stable. I think that the way Petrucci says to remember it is by taking the absolute value. No, you can't take the absolute value, can you? I forgot. All right, and so what would you expect to have the highest electron affinity on the periodic table? The highest electron affinity I would expect would be fluorine. Right? Fluorine is the most powerful oxidizer, and a powerful oxidizer, what do oxidizers want? All oxidizers want electrons. So I'd expect highest fluorine, the lowest helium. Helium.
Why did you say that chlorine is the highest in electron affinity?
He said expected. Expected is different from reality.
Yeah. Yeah, we expect, well, actually, let's just stick with the highest. We're not going to worry about the lowest. The highest is going to be fluorine because fluorine is the strongest oxidizer. Fluorine is small, right? I mean, if we compare fluorine with chlorine, chlorine is big. Fluorine is small. So fluorine is going to have a greater Z effective. And so what we're doing is we're completing the P subshell. Fluorine has 5 electrons in the P subshell. If we add a 6th, then it's complete. And then we have that octet, right? Same thing with chlorine. And so I think fluorine's going to have a higher Z effective, so it's going to be attracting electrons more. Does that make sense? Unfortunately, that's not it. It turns out that fluorine is not the highest. The highest belongs to chlorine.
No, he said expected. Right, Dr. Shibata?
Yeah, expected.
He's going to trick you on the test again.
No, I don't want to trick you on the test. This is one of those ad hoc type deals, ad hoc. Do you know, after the fact kind of thing? Because I would have gone fluorine, for sure. I would have gone fluorine. But why it is not fluorine is because electron affinity is not just the ability to attract an electron, but also the ability to accommodate and hold that electron. And so there are 2 parts to electron affinity. One, the attraction. Well, fluorine beats it. Fluorine's going to have the strongest attraction for an electron.
Can you repeat? Electron
Okay, there are 2 parts to electron affinity. The 2 parts are 1, to attract the electron, and 2, to hold and accommodate that electron. So fluorine can attract electrons, but the problem comes with accommodating the electron. there's not much room for the electron, because when we think about accommodating an electron, where is that electron going? It's going into a half-filled p orbital. And so if we look at fluorine, okay, fluorine has a p orbital like this. There's an existing electron here. A second electron comes in here, and we fill it. Whereas when we look at chlorine, chlorine's got not the 2p, but the 3p orbital. Maybe this is over-exaggerating. But the point is, here, there's going to be less what in chlorine than in fluorine. There's going to be less, well, actually there's more space. There's more space, meaning there's less crowding, right? Less crowding means less, not necessarily collisions, but less repulsions. Right. Both of these have the same charge, and so we always got to worry about repulsion. They're going to be attracted to the nucleus. The nucleus is going to be, positive charge density here, positive charge density there. So they're both attracted, but they're going to repel each other, while still being attracted to the nucleus.
So more repulsion in there.
So more repulsion here. So we say greater electron-electron repulsion. Does that stabilize things or destabilize things? It destabilizes, so the energy goes up.
So it's greater repulsion because it's smaller space?
Yeah, smaller. 2p versus 3p orbitals. 3p orbitals, no big deal. So, okay, what about bromine and iodine? When we form bromide and iodide, once we get there, then the orbitals are big enough that we don't care about repulsions anymore. And so if we go from chlorine to bromine, the orbitals are so big that there's plenty of space, and so all we care about is attraction. And so chlorine's a smaller atom, bromine's a bigger atom, so it's easier to attract. The nucleus has an easier time attracting it if it's closer. And so this is the only exception here, and that is fluorine and chlorine. The rest behave as you would predict. So again, once we get to chlorine's size of orbital, then electron-electron repulsion is no longer a factor. And so bromine's going to have a much bigger orbital, but chlorine is plenty big enough. No problem. It's just fluorine. Fluorine is a high Z effective. This is why it's a great oxidizer, right? But that pulls in the orbital so tight that things get crowded. And as things get crowded, then we get these. It's not a huge difference. In fact, they're very close, But it just so happens that chlorine beats it out. Are we ever going to use that tidbit of knowledge? No. We're not. In fact, the only thing we're going to do, and I don't know if maybe I'll ask you a question about it, but the only thing we're going to do is we're going to do calculations, energy calculations. And so that's what we're going to use the numbers in Chapter 9 for. The sizes, we want a qualitative idea, but for ionization energy and for electron affinities, we're actually going to put those numbers to use. And so let's take a look at a reaction here. So if I take some magnesium solid and some oxygen gas, what can I form?
Magnesium oxide?
Magnesium oxide, MgO. Did I do this reaction? The magnesium strip, burning it? Yeah. Gave off that. Do you remember the light the burning magnesium gave off?
Yeah.
Bright white. Bright white means it's a. Does it have a what would you say, line spectrum?
Yes.
Or a continuous spectrum?
Continuous.
It has a continuous spectrum, meaning that the electrons can pretty much get excited to any energy. Now, why is that happening in magnesium there, whereas didn't happen for the hydrogen lamp, or some of the others. Right. It's because the electrons were pretty free, you know. Electrons are pretty free. Are electrons pretty free in metals usually, right? They aren't really constrained. In other words, they have a lot of space. If they have a lot of space, then, you know, is it big compared to the wavelength of the electron, or the space, that is? It's big. And so that quantization effect isn't so significant. In other words, I think with magnesium, we're looking at molten magnesium metal, probably. It got that hot, and then the electrons got excited in that metal and started emitting white light, pretty much. Yeah. Well, anyway, going back to this, here's how we use the numbers from chapter 9. In order to make magnesium oxide, what do we have to do to magnesium? Well, in order to make magnesium, we have to take magnesium, right, and then form magnesium 2+. In other words, magnesium's got to lose electrons. Does this happen in one step? No. It's going to happen in two steps. And so this is the way we'll break it down. Okay, magnesium goes to magnesium plus. We call this I1. How much energy does that cost us? Actually, does somebody have their book handy? You could look it up. And then magnesium plus, in turn, gets ionized to, and we call this I2. I should have grabbed the book. And so let's get some numbers on there, because let's do some calculations here. Let me bring up the book here. Is it going to be, what do you think, I1, is it endothermic or exothermic? It's exothermic? Okay, exothermic means it costs you energy, or it releases energy. Exothermic means it releases energy. So is forming Mg plus going to be energetically favorable or energetically unfavorable? Actually, in order to pull an electron off magnesium, that's going to cost you energy. And so it turns out that I1 is endothermic. But in fact, all ionization energies are endothermic. But we know that magnesium is a good reducing agent. Why is it a good reducing agent? It's not a good reducing agent because it's exothermic. It's a good reducing agent because I1 is not. In other words, things like sodium. Sodium is an excellent. Did I talk about this? Sodium is an excellent reducing agent. It's a powerful reducing agent. In fact, water is strong enough to oxidize sodium metal violently. Is that because sodium really wants to lose an electron, so it gives it away for free? In fact, it pays you to take the electron. This is what exothermic says to me. If this were exothermic, then magnesium is paying me to take the electron away from it. Does magnesium pay the oxidizer to take the electron away? No. Magnesium, it's going to cost the oxidizer some energy to oxidize. And the same thing with sodium. Do you guys recall, did I talk about this? Sodium has an ionization energy of about 500 kilojoules per mole. And so, you know, it doesn't pay anybody. It makes It makes the oxidizer. So water had to pay 500 kilojoules per mole to take that electron from sodium, roughly. Which means powerful reducers are what?
Expensive.
No. No. Cheap. Powerful reducers are cheap. So 500 kilojoules per mole to take an electron from must be cheap. Otherwise, how could water afford to do that? And water is not very reactive, is it? And so we have to put some perspective on the numbers. And so let's take a look at some of these numbers here. Did we look at the numbers earlier?
Yes.
Why?
It's easy to use an electron. Doesn't take much energy to take that electron.
All right, here. Do you see the powerful reducers? Lithium, sodium, potassium, rubidium, cesium, francium. They all cost you energy. But when you look at the energy, like sodium is about 500 kilojoules per mole. Francium is less, like 400 and something. And these all react violently because the cost is quite low. And so it doesn't cost you much energy to ionize these, but it still costs you energy. Whereas something like helium, is that easy to ionize? No. Helium isn't so easy to ionize because it's going to cost you quite a bit of energy. The first one there. And so these are good reducers because they don't cost much energy to ionize.
Can you elaborate on that? Why reducers are cheap? So reducers lose electrons.
Reducers, are they free? Free would be zero energy. What's better than free? What's better than free is if somebody pays you money to take their new car off the showroom floor. Right? Is that going to happen?
No.
No. And so a lot of people think that reducers give electrons away. Do they really give electrons away? Is anything really free? No. It's just that it's so cheap,
Okay.
they're easy to take. That's all, in terms of energy. And so, in fact, a lot of people memorize reducers. Reducers give electrons away, but they really don't. Yeah. It's really going to cost you some energy.
Oh, I put my eyelashes on it. Are you okay, Adam?
Yeah, I need some numbers here. So how much energy does it cost to take the first electron from magnesium? About 738. Let's just round it to 738. The second electron?
1400.
1451. The third electron?
7,000.
Did we talk about why?
It's closer to the core, right?
It's a core electron. Core electron is going to cost you significantly more energy. And so the thing is, here, is magnesium plus 1 possible? Yes. Is magnesium plus 2 possible? Yes. Is magnesium plus 3 possible? Yes. It's possible, but is it likely to happen? No. Why? Because it costs too much energy. And so let's talk about this for right now. Oops. So we have I1 for magnesium, 7733. So let me turn this off here. 738. 738 kilojoules. Is that a lot of energy? It seems like a lot of energy because 738 kilojoules, that's got to be a what? A red photon? Kilojoules per mole. What do you think? A violet photon? No, violet photon, probably the most energetic violet photon's around 307 kilojoules per mole. This has got to be at least a UV. So we shoot a UV photon here, knock off the first electron. To knock off the second electron is going to cost you more energy, 1,451 kilojoules per mole. 1,451 kilojoules per mole, well, that's got to be what? That's probably UV, high energy UV, a higher energy UV. Does it make sense? The second electron is going to cost you more. You got the same number of protons, but now fewer electrons, so there's going to be a stronger electrical attraction. The remaining.
How much
And
is that?
What's that? 1,451? Yeah. Okay, now we could use something called Hess's law to do what?
Delta H.
Yeah, we're going to figure out how much energy it costs to go from magnesium to magnesium 2+. Okay. And so the amount of energy that it's going to cost, we just sum up the steps. It's going to be 1,589. Wait, is that right? 1451. No, maybe not. Right. 8. That's going to be 9. 7 and 4 is 2189. Wow. Okay, there we go. 2,200 kilojoules. Huh? 2189. Thank you. 2189 kilojoules just to form a magnesium 2+. You think that's easy to do? You think water could do that?
No.
No. And so we got to expend some energy here to do that. The funny thing is, for ionization energies, what state is this? Is it solid? Magnesium's normally in the solid state, but for I1, it can't be. For I1, it's got to be in the gaseous state. That's the strange thing about ionization energy. Ionization energy is defined for the gaseous atoms or the gaseous ions. And so we're stuck with that.
And then the ions that it produces, for step 1 and 2, is that still a gas?
Yeah. They're all gases. Now, the weird thing is, why does this happen? If it costs this much energy, why is it going to happen? Because normally when we look at the ions, it's easy. You know, magnesium 2+, calcium 2+, aluminum 3+. We know the ions are going to be formed, but when we look at the energetics of this, it doesn't look so good. And now, you know, it's going to cost us quite a bit of energy to form Mg 2+. It just doesn't seem so favorable. Not only that, we aren't factoring in all the energy because this is Mg in the gaseous state. We don't start off with Mg in the gaseous state. We actually start off with Mg in the solid state. And so how do we get from Mg in the solid state to Mg in the gaseous state? Well, first we got to take Mg in the solid state at what temperature? At room temperature, and then we have to do what to that? We have to add heat, right? So we're going to add some heat to this to do what? To boil it? Does magnesium boil at room temperature? No. We need to add heat to warm it up to Mg solid at the boiling point? No. Actually, we have to go to something called the melting point, right? And so what we're doing is we're going to heat up a chunk of magnesium from room temperature up to the melting point. Q is equal to what?
MC delta T.
Yeah, Q is going to equal the amount times C times delta T. In other words, we're heating an object. And then I need some more room here, so I'm going to tilt this up. I would go across here, but I didn't make enough space because next we go from magnesium solid at the melting point to magnesium liquid at the melting point. And so what we're going to do here is we're going to melt the solid into the liquid. When we melt it, the amount of heat that's required to melt magnesium is equal to amount times C times delta T? No. It's going to be the amount times delta H. Now this delta H has a name. It's either called melting or fusion. Fusion means melting. And so this is delta H of fusion. So amount times delta H of fusion. Now once we have magnesium liquid at the melting point, now can we vaporize that into gas? No, we have to heat the liquid up to its, well, the vaporization temperature we call the boiling point. So we need to heat up the magnesium liquid up to its boiling point, BP, the temperature at which it boils. The amount of heat required to do that is called what? Q is equal to the amount times what? C times delta T. So we need the specific heat or the heat capacity of magnesium liquid. Now we have magnesium liquid at its boiling point. Now what do we have to do? We have to vaporize it to magnesium. See, I ran out of room here. Magnesium gas at the boiling point. This is the amount of heat required to do this is Q equals amount times delta H of, yes, vaporization. Vaporization is for boiling. We'll call it delta H vap. And then we have to go to, actually, is that it? No, because this gaseous magnesium, what temperature is this table at? Probably. It's probably at 298, although it's tough to get magnesium gas as a gas at 298. And so we could be done here if this is at the boiling point, but it's probably not. This is probably at RT. And so we have to cool it down. But anyway, we'll just leave it at that. So in other words, does heating the solid cost you energy or does it release energy? It costs. Does melting the solid cost energy or does it? It costs. Does heating the liquid cost energy? It costs. Does boiling the liquid cost? It costs. Cost. Everything costs energy. Why is this favorable? Why do you even want to go to magnesium 2+? Why not just leave it alone as magnesium and just be happy with it there and not have it cost so much energy? Right? Not only did we factor the cost correctly, because I want to ask you this. We're going from magnesium liquid to magnesium gas. A liquid doesn't occupy much space, but a gas occupies a lot of space. So the first thing I think about, liquid to gas, we got to think about change in volume, which means we got to think about work. I'm only doing Q here. What about my work? Is the work going to cost me even more?
Yep.
Do I need to calculate it?
No.
True or false? The work is going to cost me. And is the work going to cost?
Yes.
Yes, because we're going from small volume to big volume. So the system is expanding. So is the work going to cost energy? Yes. Yes. Do I have to calculate it and then add it to my Q?
No.
Why not?
Negligible?
No, it's not negligible. It's significant. Do I have to calculate it and add it to my Q to get an accurate?
It's just heat. It's already been done. It's not
Huh?
thermal energy.
It's already been done. How could it have already been done? I'm just calculating Q here.
Internal energy.
I'm just calculating Q. How could it have already been done? Hmm? Because we're using delta H, that's one reason you could say it's already done. The other way you could say it's already done, it has already been done. Because if you drilled these charts into your mind, you know, the internal energy chart, remember these? Do you have these drilled into your mind? Generate the internal energy diagram for this. Magnesium liquid going to magnesium gas. For me. Go ahead and do that right now. Can you?
Yes.
And do you see, has it been done or has it not already been done? So does somebody want to explain it to me? In other words, do I need to do let me ask you this, true or false? I need to do a second calculation for this step here because I need to factor in the work. True or false?
Isn't the work already factored in because delta P of vaporization includes the amount of work done?
Yeah, but I just have Q here, right? If I just have Q here, isn't there a W term also?
It's not constant volume.
Well, I'm calculating Q, and I know that there's a W as well, right? And I know W is not zero. W can't be zero here because what's happening with the volume? It's increasing. In fact, is this an endothermic process or exothermic process? It's endothermic, so we're starting off with magnesium liquid down here, and we're going up to magnesium gas up here. And there's a delta U here, which is equal to Q plus W. I need to know my W, don't I? In order to figure out how much, you know, I want to figure out how much energy this is going to cost me. And so don't I need to know, because is my W zero?
No.
My W is not zero. Definitely some work is being done here. And so my question is this. True or false? I need to do a second calculation for W in order to figure out how much energy I need to input into this. False. False. Why?
Because delta H is equal to delta U plus.
Well,
Well, if you draw the chart, the work is going down, right? And then, because it's done by the system, so work is going down.
okay,
And
work
then-
is going down.
And then Q is going up.
Q is going up.
So that means there's more, delta H is greater.
Right. You see, That's good. That's the answer I was kind of looking for. The answer is it's already factored in. The work is already factored in because otherwise you'd have to input less heat than, if you did this under constant volume conditions, to vaporize the magnesium like this, to boil it, would cost you less heat. The reason it costs you less heat is because you don't have to do any work. And therefore, here, the work is factored in. The work is factored in. This is like this. You have to shift your way of thinking here because what delta H is and what Q sub P is it's like the out-the-door price. When you go shopping and you look at an item and you see its price, you have to do a mental calculation, right? That's not the price you're going to pay because when you get to the cash register, they're going to add a tax to it. And so really the price you see there is not the price you pay. The price you pay is a little more because of the tax. Well, here's our tax, right? And so the price we just paid was a little more because of the work, the tax. Right? This is what delta H is. Delta H is what we call the out the door price. It's the tax is already factored in, right? It makes working with energy easier. Can you imagine having to do every single calculation? You have to calculate the tax. Isn't it much nicer? Because the tax, can you avoid the tax? No, you can't avoid the tax. And so you might as well just get the energy value with the tax included. And so you get the tax included price. Does that make sense? Yeah. But it's not always a tax because sometimes you have those tax-free days, like what was it, Memorial Day sales. Sometimes they do tax-free, right? And the retail price is the price you get, right? But that's okay because delta H is the out-the-door price, Or sometimes there's a sale, And what's the price after the discount? Well, delta H is the price after the discount. And so when you're thinking about delta H, what I call delta H is the net energy. The net energy is what you're actually going to put in your pocket or to put in your bank versus the gross energy, which isn't necessarily the price you pay. Does that make sense? And so these are the things you keep drilling, or at least trying to think of new ways to understand them so that it clicks. And so, for example, if you had these charts so drilled down, you would have seen, work is going down, therefore heat's going up, so the heat's already incorporating the work. So we don't have to do a second calculation here for the work. Okay. All right, now back on topic. Back on topic is cost energy, cost energy, cost energy, cost energy. This is all costing energy. When are we going to get some energy return? Do you always want to be paying? No, I don't. Actually, I was talking to a friend of mine, then I didn't know he was a big horse racing gambler. But he said, the first time he won a huge amount of money. And ever since then, he was addicted to it, and then eventually quit. But, I never became a gambler because every time I went to Las Vegas, I always lost money. Lose money. Pretty soon I just gave up because it's just not worth it. And so why doesn't nature just give up? Because this is just costing energy nonstop, right? To form magnesium 2+. Forming magnesium 2+ doesn't sound as great as it once did because when we're looking at the periodic table, it's easy. Lose 2 electrons, be the same as neon, which is very stable. It's got that stable Nobel gas electron configuration, right? And so, well, let's see what's happening with oxygen. Maybe oxygen is where we're going to get some benefit. And so let's take a look at oxygen and see. And so what does oxygen have to do? Well, one thing oxygen has to do is oxygen is O2. So if we take a half a mole of O2, we have to break the bond. And so we go from a half mole of O2 gas to a mole of oxygen atoms. Is that going to cost us energy or is that going to release energy? It's going to cost us energy. How much energy is this going to cost us? So let's take a look. Q is equal to the amount times we call this delta H of bond, the bond energy. And so, for example, a carbon-carbon bond, do you know about how much energy it costs you to break that bond? 347 kilojoules per mole to break a carbon-carbon bond. Let me ask you this. Do you think it's easier or harder to break an oxygen-oxygen bond? Harder. Why? Because oxygen is bigger than carbon?
Oh no, it holds the electron.
Oxygen is smaller than carbon. And so if you're thinking about breaking the bond, is it easier to break the bond from smaller or from bigger, right? Bigger. And so oxygen should be greater than 347. It's in the 400s. Okay, so it's going to cost you quite a bit of energy to break this bond, but that's okay because we got to get some energy back, right? And so this is, about what? This is a half a mole, so let's say it's about 400 kilojoules per mole, so we're looking at about 200 kilojoules worth of energy to break that bond. But now we have oxygen in the gaseous state, and now we're going to go to oxygen in the gaseous state with the negative charge, so we're going to add an electron to that. This is called EA1, and this is exothermic, right? EA1s are mostly exothermic, so let's see how much energy we get. I'll look that up here in our book. Minus 141. This is minus 141 kilojoules per mole. And so far we've used up about 200 kilojoules. We get minus 141, EA1. Then we got to go to EA2 to go to O2 minus. And so this is EA2. Well, let's see what EA2 is for oxygen. (744 kilojoules per mole) plus 744 kilojoules per mole. So this is going to be about plus about 200 kilojoules per mole, assuming that oxygen has a bond energy of about 400 kilojoules per mole. So this is going to be 200 kilojoules per half mole. Sorry. Positive. And so this gives me about positive 50 plus another 750. That gives me about plus 800 kilojoules. Does that sound very favorable? No. And so why the heck does magnesium and oxygen want to react? Because it costs so much energy to form the ions. It just doesn't make sense. Why doesn't oxygen stay as oxygen? Or, oxygen shouldn't stay as oxygen. Oxygen should go to oxygen -1, not oxygen -2. Right? Oxygen should just stop here because that's favorable in terms of energetics. And so the question comes up is why bother forming magnesium 2+ and oxygen 2- when it costs so much energy? This is like if you keep going to Las Vegas and you keep losing lots of energy, losing lots of money, eventually you might give up. Eventually you might win. So is that what nature's counting on? The Heisenberg uncertainty principle? Here, this tremendous uncertainty in the amount of energy is involved here. Is it? No. And so let me tell you where the return comes in. The return comes in here. Magnesium oxide is not gaseous magnesium ions and not gaseous oxide ions. Magnesium oxide is when we take the gaseous ions like this and combine them. When we combine them, then there's a huge energy refund to form magnesium oxide solid. And so here's the return. This delta H is highly exothermic. In other words, when we form the bonds, we get the energy back. Well, let's take a look at the structure for magnesium oxide over here. Magnesium oxide, what kind of compound is this? Would you say it's an ionic compound, a molecular compound? Ionic compound. Ionic compound is going to consist of the ions, and so what we have here is something like this. If we think about magnesium, let's see, magnesium versus, actually we aren't going to do it just yet. But we're going to have magnesium ions and oxide. What do you think is bigger, an oxide or a magnesium?
Magnesium.
Ion. Oxide. And so magnesium 2 plus is probably small like this, and then we'll have an oxide like that. Ionic compounds form ionic bonds. And the way we show ionic bonds is just this. We have a positive ion here being attracted to a negative ion here. And so it's just an attraction between this positive ball and the negative ball, and they're going to come together and stick like that, like two magnets. That's it. But the interesting thing about this is it doesn't just form one bond. So if you're a positive magnesium, you want to surround yourself by as many negatives as possible. And if you're a negative oxide, you want to surround yourself with as many positives as possible. And so what we end up with here is something called a ionic lattice. Which I'm starting to draw here. And so this would be called an ionic lattice. Now, if I have a mole of magnesium oxide and I want to break the bonds, let's say I want to melt it, do I just need to break 1 mole of magnesium oxygen bonds? If I have a mole of magnesium oxide, it turns out I have to break a lot more, because each magnesium is actually bonded to not just one oxide, but each magnesium is bonded to 4 oxides here in the plane. And not only that, this is a 3-dimensional structure, so we're going to have 1 oxide on top and 1 oxide underneath. And so it turns out that each magnesium is bonded to something like 6 oxides here. But it gets a little bit more involved, because each magnesium is bonded to what we call 6 oxide nearest neighbors. And then the next nearest neighbor is a magnesium, so it's repelled by the next nearest neighbor. But the next nearest neighbor is a oxide. So it's attracted to the next nearest neighbor. And to the next nearest neighbor is a magnesium, and it's repelled. And then the next nearest neighbor is a oxide, and it's attracted. And so this is what we have here. When we think about this is called a lattice. When we think about the lattice energy is not equal to the bond energy. It's not just one bond we're breaking. In other words, we have to break a lattice of bonds. And the lattice of bonds is you sum up all the attractions and subtract out all the repulsions, and net you're going to have a very strong lattice. Not necessarily a very strong bond, but a very strong lattice. And so this is what we see here. This is the delta H of the lattice. We get a lot of energy in return by forming this network here. And so yes, it did cost you a lot of energy to form the ions, but you get a lot of energy in return. Well, you know, let's look at a cost versus benefit analysis. In terms of a cost versus benefit analysis, what if we didn't go all the way to 2+? What if we stopped here at magnesium plus? That means our initial pay-in cost is less. And then, rather than going all the way to O2 minus, what if we stopped here at O minus? Look at that. That's favorable, right? So if we made this Mg plus and O minus rather than Mg2 plus and O2 minus, our initial cost is smaller, right? The initial cost is smaller, but the return is less. This is like, I don't know if you into gambling. Maybe I shouldn't use gambling analogies for some of it. But if you are at the penny slot machine, are you going to expect to win big?
No.
No. And so the same thing here. I mean, if it were a +1 and a -1, that is, if we drop the charge to +1 and drop the charge to -1, what would that do to one of these bonds? It'd be weaker. How much weaker?
Half.
Would it be half?
No.
It'd be 4 times weaker. 4 times weaker, because if you double it, it's 4 times stronger. Coulomb's law. ZA, ZB. Well, you know what? Then nature should do this. Nature should just pay a little more. Because if we went to Mg3 plus and we go to O3 minus, then the payout is going to be a lot bigger, right? Yeah, the initial cost is going to be bigger, but if this were instead a lattice made up of magnesium 3 pluses and oxide 3 minuses, how much stronger is the bond compared to +1 and -1? 9 times stronger. 9 times stronger means this lattice energy is going to be huge. We're going to get a huge drop here because that lattice is going to be so much stronger. Right? The bonds are going to be a lot stronger. And so why doesn't nature do this?
Efficient.
It's not cost effective because forming magnesium 3 plus, you know, this was what, 1400, 1500? This is 7,800 kilojoules. It's too expensive to make magnesium 3 plus. We'd have to ionize a core electron. And here, this is way too expensive. The EA for this is going to be hugely endothermic because that third electron is going into the next shell. And so this is not beneficial at all. And so this is the reason why in chemistry, what you want to do is you want to maximize the charge so that you can make the strongest bonds. So maximize the charge so you can make the strongest bonds. Well, maximizing the charge using our periodic table means just dealing with the valence electrons, because if we start going to the core electrons, the cost of maximizing the charge is too great. And so this is why the octets work nicely in the noble gas, you know, what you guys learned works nicely. You know, it's going to stop here because adding another electron beyond this is going to go in the next shell. So chlorine is going to gain 1, but it's not going to gain 2. Even though you could form a stronger bond, it's just going to cost too much energy. And so we stop here. Magnesium 2 plus and oxide 2 minus. In other words, this becomes isoelectronic with neon, this becomes isoelectronic with neon, and we stop. It's not the stability of the octet. You know, some people say oxygen wants 2 electrons because it gets an octet, which is very stable. Is it? Really? When you look at the electron affinities, is oxygen having an octet stable? Technically not, because this is going to cost you energy. The reason why oxygen wants an octet is to maximize the charge so that it can form the strongest bond possible. Does that make sense? And so this is why we look at the numbers for the energy, because the numbers for energy will give us more insight into, you know, why is oxygen a -2 ion? Why isn't it a -1? Why isn't it a -3? You know, well, we know the pattern in the periodic table, but this and the energies will help us understand it better. And so let's stop here, and then we'll start with the next chapter. So this ends pretty much chapter 9 with this. I'm going to skip some of the latter